Okay. Good morning, everybody. Uh, Today we are going to first talk about the one of other algorithms that is famous in Islam, and we will see uh, how it can improve the existing techniques that we studied so far. But also we will see that there are some problems with the algorithm that we are going to see today. The algorithm is particle filter, and today we will focus on the particle filter localization because it can be used in different techniques and in solving different problems. But we will see how we can adopt particle filter in order to solve localization problem. So in this chapter, first of all, today we will talk about the algorithm itself, particle filter. Then we talk about the Monte Carlo localization that comes from, and basically the general idea is based on the particle filter. And we also talk about the FastSLAM, and we will see how we can use benefits of the existing techniques that we studied with particle filter in combination together. Also, of course, we will talk about one of the techniques of FastSLAM. For FastSLAM, there are multiple different techniques that, depending on the application, we can use them. So first of all, let's have a definition of what we want to see. We say the particle filter is alternative non-parametric implementation of the Bayes filter. So if you remember, we had some techniques that they were non-parametric. And it means that we are not relying on Gaussian distribution on mean and the covariance. So based on that, we have non-parametric technique still over here too. So what is it doing? First of all, the basic benefit is that we are removing linearization that we were doing in other algorithms. For example, in uncentered Kalman filter, we had to do linearization of the nonlinear function that was costly, and we did lots of effort in terms of mathematical equations. But luckily, we don't have that complexity over here anymore. What is happening with particle filter? We say it is approximating posterior by finite number of parameters. So it's looking like the histogram filter, but we do it in different ways. In histogram filter, we were making grids of the distribution, and we were allocating probabilities to each grid. But now we want to do something else. We want to increase the accuracy with particle filter itself. So if you wanna then have a look at the beginning, the differences with the histogram filter that we studied, we say how the parameters generated are different, that we will see how they can be done, and how we can distribute it in the environment. So for now, you can consider we have some particles that we will define what those are, and we don't want to drop them as probabilities on each one of the grids that we make grid of the environment anymore. So the key idea is that we want to represent the posterior belief that we already know by set of random state sample that are drawing from the posterior itself in order to calculate the prior. How this is happening visually, we can say, okay, let's have this distribution or nonlinear function of f that we already know that. We cannot use this form of distribution in our algorithms, like extended Kalman filter or uncentered Kalman filter. Why? Because it was not Gaussian. And what we were doing, we were converting this to the Gaussian distribution. Later, we were able to use it. But now here, we want to kind of, if you have a look here, we want to kind of have the particles that they are showing the density of this probability distribution function that we have. So how dense they are, for example, here the probability is higher, we have more dense and much more particles over there. That, of course, this is not directly using a particle filter, but this is the idea that kind of says instead of saying how likely where the robot is, if you think about the position, then instead of having this probability distribution, we can throw it out and we can say how dense the points are here. Then we can understand the same concept by number of particles that we can call here. Is it clear here, this part, for everybody? So, for example, here we have less points. Less likely, if we talk about the localization, less likely robot will be here. Most likely robot will be here because this is denser. And this represents exactly this distribution for us. So that without any effort of conversion of the Gaussian distribution, we can show the same scenario with particles. But of course, it's not that easy. We will see what else and what we should do or what are the procedures. But this is the general concept of, for example, in the localization, what we can do. So the point is, as I explained to you, instead of representing distribution by parametric form, we can show density of the normal distribution so that it represents distribution by set of samples drawn from the distribution, that we can call them as these blue points as samples too. So the particle filter represents approximation, but is non-parametric. Why approximation? Because of course when you are converting that distribution to samples, then you may lose some data depending on how many number of samples you have. Because here when you have distribution itself, it means that, like when you have this, it means that for each one of these points you have exactly the samples, if you call. And the idealistic way is like plotting all of these to samples, but that's not that's what we want to avoid. We will discuss also. Because of that, it is the approximation, so that we can say it can represent much broader space of the distribution. One, of course, simplest one is Gaussian, but nonlinear functions can be represented too, as we shown. And in particle filter, samples of the posterior distribution are called particles, as you will see over here. So we say we have set of particles. So each particle is a sample from the environment that we have. Okay? So we call it sample of posteriors. So we have set of samples, that this set of samples includes each identical sample in the environment. For example, xt1, xt2 up to xtm. That for example, each one of each particles can be represented the true value of the, for example, robot pose. That robot pose can include the x, y, theta, for example. So each of my particle, now you can imagine that says, like, if my robot is here and I can have many particles, that the pose of them are different in the environment, and that pose can be the x, y, and theta. So that represents how likely where my robot is and what is the orientation or angle of robot heading to. Clear? So we say m, what point I have here, m is number of particles in the particle set, and usually is large number. This m indicates how many particles if I want to have in the environment. So the rule of the including a particle in set xt can be defined by, if we say ideally the xt should be proportional to Bayes filter posterior belief, it means that if we want to like ideally present exactly what is the distribution, we should plot and bring all the points exactly to don't lose the data. And if you have Gaussian distribution, for example, then the sample set or particles should be exactly representing the same distribution. That is too high if you want to do that. Because of that, what we want to do, we usually have lower samples. Instead of having like millions of samples, we can say, okay, just having like 10% of samples can show my distribution still. A few should be enough to show the same concept. So that sampling can look like this. We can say in the set of XTM, set of particles that I can have, we can bring, how we can bring particles inside, the probability of the XT given by observation and control command. So that generally it means that we want to sample particles with the probability occurrence that we have. That can come from observation and control command. It means that the distributions that I have indicates the probability of the pose of robot, that distribution that indicates the pose of robot can help me to choose the samples that I want. So it means that when my observation says, okay, I see some environment, most likely robot is here, that previously our probability distribution Gaussian was like around here, right? So if it's 2D, it's like around here. Because my observation says most likely robot will be in this Gaussian distribution. So now if we want to bring it to sample form, we use the same probability concept to sample this time instead of having that distribution. That can come from two sides, observation or control command or odometry. That they have also different distributions also, but they can help me to sample from environment. Or better example, like if I'm the robot moving in the environment and now I know the particles, and if I want to sample, how those samples I would choose the samples that more likely says I'm here. I would like to have examples or samples of the particles of the problem that indicates where the robot is and where the pose of the robot is. So we say a subregion of the state space with more populated samples is showing higher probability of the robot true pose or state. So that those particles, when the robot is here, if it's more populated here and in that corner there is no, I can say more likely robot is. So all the concepts that we discussed are same, just we remove the, for example, Gaussian distribution as representing a mean and covariance where the robot is with particles so far. So similar to previous techniques that we've studied, particle filter also is relying on the Bayes filter technique, Bayes filter algorithm, and it constructs the beliefs of the where the robot is in recursively form of the belief based on the previous belief on the time step that we've crossed. So same concept, predicted belief and belief, that we can also say the belief of xt and belief of the xt minus 1, that the whole calculation, it comes from here. And it means that when we talk about the Bayes filter, it means that robot believes that previous calculations was correct and all calculations comes from previous calculations. And we have online SLAM again. So all the calculations is online, not in considering all time series of previous occurrence of the particles where they were. Of course, we can consider those too. Then, if we consider those, then it will be it will not be online SLAM anymore. As you realize so far, now the beliefs are set of particles, And the particle set xt comes recursively from set of previous particles. So here we had the belief. Here, then we talk about the particle set for everything. So it means that in time t, we have environment, map of environment. We have lots of particles. Each one represents where the robot is and where it is heading. And time t plus 1, we want to kind of play with those particles to see how we can update the new particle sets. We will see how to do that. It means like kind of robot is at time t, something happening, robot is moving, observing new data, then previous particle set, we should think how we can update those to new particle set to more likely say where the robot is. So now we want to talk about the steps of particle filter. Step by step is simple. Let's see what's happening. First of all, we say randomly generate a bunch of particles in the environment. It's like seeding, like distribute particles in whole environment, considering that we don't know where the robot is. So it can be uniform distribution of the, like something similar to what we were doing in histogram filter. We were giving the probabilities of the equal probability to each one of the grids at the beginning. Here also the same, distribute the particles to the environment randomly. So that if we want to solve SLAM problem, localization problem, we have position, heading, and also the weight. So position says, okay, where the xy, heading is like the theta, and the weight says the probability or how likely that particle is important also. That is, it is also the one element that we want to calculate. So after first step, randomly generating bunch of particles, we have a prediction of the next state of the particles. That to do that, we move the particles based on how the prediction of the real system is behaving. For example, if our robot, we have lots of particles, and our robot moving forward, of course, most likely all the particles should move to the upside. Because we know that our robot is moving one step forward. So most likely my particles also should shift to the up. So now, similar to histogram filter, you can also think that if we put lots of particles in the environment, and if your robot is moving to this side, all the particles move to that side, finally they stop at the end, right? And if I'm moving for a long time, finally also particles will be collected there. So with this concept, only with odometry you can see that, okay, this makes sense. Then those particles will be collected there, and more likely your robot is there too, because all the time moving to the left. So this is the general idea of this step. So after prediction, similar to Bayes filter, we have the update step. In update step, what is happening? The observation is coming from environment, and the observation changes here the weighting of the particles based on the measurement. So here the weight says which one of the particles is most likely the particles that we want. We are not updating the position of particles anymore here like previous ones. Here we say, okay, update the weights of those particles that we moved. How likely, which one is representative of our robot most likely, depending on observation. That can, again, rely on the pose. That pose includes position and the heading direction of the robot. Is it clear, this step? So here we have differences with previous techniques. In all previous techniques, observation, we're updating, correcting the last step of the odometry. So we had the motion model moving, and every step we were updating the data over here, there too. But in particle filter, we are updating the weights instead of correcting the pose of those particles. We don't want to move those particles anymore, just we give the weight. So, and last and most important step is resampling. Resampling says, okay, now we did it. in one iteration, robot moved. At the first, we distributed particles. Robot moved. We shifted particles based on the odometry or motion model. Then, based on the observation, we gave or changed update the weights of each one of them. Which one is more likely the particles that we have. After that, now we need to resample. Resample means that for next generation or for next step of particles, which one of these particles should be chosen to move to the next step. And that's called resampling, and we want to discard the particles or choose the particles that have higher probability to be the robot pose that we have. So if I draw something a little bit visual here, we can say if we have the environment and if we distribute uniformly particles that each one has 3 elements of x, y, z, theta, then after I run the motion command, like move to the right, all the particles will be shifted to the right, so that I can remove, for example, this part over here, let's say all shifted for simplicity, and we have more here. After that, wherever the robot is, we don't know so far, but it's like after observation, robot was here and observed like some elements of the environment, then the particles inside this part will gain more weight. The W of these ones at the beginning were equal, but they will increase. After increasement, of course, as simple problem, we can say, okay, based on the observation that we have and the weights that we have more likely here, more likely robot should be here because the weights of these particles are more. It means that more likely one of these particles representing where the robot is. So because of that, in next step, if I draw it down, I would like to resample the particles more likely around here that represents robot location. So I would like to resample from here more likely and less from other ones. And this is how we can say, okay, where the robot is, and next sample set will be more likely representing my steps. Any question? Is it clear? So we also have one step of computing the estimate that computes the weighted mean and covariance of the particles to say really where the robot is, that it's like at the end, or if you want to really say where the robot is, you can calculate the mean of all. So here, if you calculate the mean of all, you will say, okay, you would say robot is here, right? Mean of all particles for the position. But here, now mean maybe is more likely closer. And if we continue this, motion command observation, we're gonna find where the robot is. This mean of all particles will move toward where the really robot is. Yeah?
So is the total of the particle
yeah,
same?
Yeah. The probability of the all particles, the mean and covariance says, the mean says exactly where it is, covariance says what is the error over there. It becomes like Gaussian distribution again, based on whole data points, particles that we have. So as you see, the algorithm technique looks like simple and not as complex as previous ones that we needed to do lots of math calculations, but of course there are some elements that we need to see how we can bring them into game. In order to do so, we will talk about, first of all, Monte Carlo technique as a technique of particle filter, that it says using finite number of randomly sampled points to compute the results in Monte Carlo method. So it's kind of like particle filter is general model of the algorithms. The idea is same. Monte Carlo is a technique to do that, and the idea is creating enough points to, it's like a practical way of bringing the particle filter into localization problem. We say we want to generate enough points to get representative samples of the problem, then run the points through the system that you are modeling, then compute the results of the transforming point, and then apply the Bayesian filter on the problem that we have. After doing so, we can say you can finally extract the estimation of the particles with the weights that we have. So this idea is like representing the same thing, but as I mentioned, it is a specific instance of particle filter and is applied to localization algorithm based on the particle filter. To understanding, I visualized it there for simplicity, but let's have a look at the directly how we can implement the in algorithmic mode. So in algorithmic mode of the particle filter, we have the set of particle sets as set of x's, control commands, and the observation as input. So what we do, we create a empty set of the particles at the beginning that at the beginning predicted. So this is like the current set of the particles, and this one is the new set of the particles that we want to all the time talk about, like the belief and predicted belief in form of Bayes filter. Then what we do for each one of the particle sets, we sample based on these distributions that we have. So the sampling from the sampling of the xt from the probabilities of the control commands based on the previous pose, then calculate and update the weights that we have based on the observation, then calculate then add these particles based on the set of tuple of the particle pose and the weight to the previous particle set. So previous, I mean predicted particle set. So we have a particle set. Each time we sample, new sample comes with the not only particle, we add the weight that we calculated to, we find out based on the probability distribution, and add two particle set. And after this step, we generate new particle set with weights of each one of them. Then also I put it some points here. We say generate is the same thing, and then consider the odometry motion model, and sampling from distribution comes from after applying the motion command, we have the probability distribution that it moves, and this gives us the probability of the weights as a probability that we can add it to each one of the particle and put it into the set. So and I have another point that the observation over here is calculation of the weight that is again the same idea, but also it is called as importance factor. That we need to discuss it a little bit in detail how we can bring this importance factor. Importance factor represents these W's for me, these weights for me that I include in the set, and it says it is the probability of measurement observation under each one of the particles that again can be represented with this equation. The weight is equal to probability of the observation given by the pose of the robot that I have. That this importance factor calculation is a little bit challenging, that we will see in next slides how we can bring it into the form of particles. Why? Because the probability distribution, if it's linear, if it's Gaussian distribution or linear, we can do it simply for sampling over here. But with nonlinear models, sampling from nonlinear model is also troublesome. That we will see what technique we can use in order to do that. So clear so far? we have a for loop to generate weights and particles with sampling based on the probabilities. Here I explain to add to sample for readability for you. Then we have for importance factor calculations, we say there are different approaches that we will discuss in next slides. I added for comments for you. We have another loop that says for each one of the particles what to do before each step that we need to move to the next part. What we need to do, draw ice with probabilities of the weights that we have. Actually, we are doing resampling step here with the weight probability that we have. So here we moved from particles from there to here with resampling. So this is happening in this for loop over there. Draw I of sample with probability of this W per each one of the articles that we have, and then add it to the new set of particles. So here we had the predicted set, we have the new set that is resampled. So I can write kind of, this is like predicted, this is predicted X, and this is the X if I want to represent it visually for you. Then we can return the, finally we can return the new set of the X that is representing those second one over there. Clear? Just now we need to see a little bit of more details of how importance resampling or this step can be done. So we say from the, what we have here, draw from the temporary set of the X, predicted X with resampling of the particles, and the probability of drawing each particle is importance weight that I explained to you, but how? Now you can think a little bit how this can be in algorithmic form represented. You can think about this. So if we have the probability Gaussian distribution, this is simple to bring it. But in order to bring the importance resampling, we can use one of the techniques of the drawing lottery that is called roulette wheel. So if you are familiar with evolutionary algorithms, we say we have set of solutions for a problem. So if I'm talking about a little bit evolutionary algorithms, if we have set of solutions for a problem, that each one have some, how good they are based on the objective that we have some value for each one of these. For example, if it's from 100, this is 90, this is 85, this is 2, I don't know, 50, how good they are. So we need to have a technique to do the resampling, of course, that brings it, select which one of these to new set of population that I have as solution. So similarly, same concept from evolutionary algorithm can be used here, that we have set of particles, and instead of value here, how good they are as fitness, what are the weights of each particle here. So how we can choose these in algorithmic form, not just, okay, we say the probability form. So how that can happen? One of the techniques is roulette wheel, that with roulette wheel we say you can have a distribution like this. Each one of the particles that we have can have, like if we define a roulette wheel like this, say particle number 1, 2, 3, 4, 5, and each one can have different probabilities based on the distribution that we have. Then we have a selecting point, simply, then you just rotate it. If you rotate it, what will happen? Then you have a higher probability to the particle to be chosen that has higher weight over there. So if you rotate it many times, so this particle that is more important has higher probability to be chosen. So this is how we can apply to choosing the particles from there to here. I automatically did it by choosing this one that I said these are more important with higher weight. But this is how we can implement it. Roulette is very famous. Of course, we can have different techniques. Nowadays, we have libraries to bring it in form of distribution in Python. Simply do that. But if you want to implement it yourself, you need to, for example, create an array, and inside those array, copy, for example, this element more times, number of times. If you put one time this one, maybe 2 times this one in this array, then, for example, 5, 6 times more. So if you put more elements of who is going to more likely be there, you're creating an array form of the particle filter that you can see, like each one of these segments can represent each one, that this one has more numbers. Then if you apply random selection from that one, that big array, then since you have more number of these elements, number 3, then you more likely will choose it and bring it to the next distribution. Okay, clear? Simple and practical way of doing this. So we have a problem here. What can be the problem or benefit? Can be like both problem and benefit. What do you think the problem is with the roulette wheel? Yeah?
If you have a lot of particles, you multiply this number by the probability of each particle, so it's a big array.
Yeah, that's one problem, but that we are not exactly meaning that one here, but that can be acceptable problem, yeah. But there is nothing else you can do with it. That's like the computation that you need to do. And that's actually particle filter problem, not roulette wheel, that we will discuss it later. What else can be the problem? That is also not problem, also benefit. Not only is the problem, but also is the benefit with this technique. If any of you were working with evolutionary algorithms, would answer it in a second, because that's very common problem in EEA, developing techniques for that one. No idea? Okay, the problem is that if you have a look at number 3, if I rotate 10 times, maybe all the 10 times these 3 will be chosen. Then I'm creating lots of repetitive particles from these 3, and I'm losing all these. Right? I had many particle samples. Although this probability is higher, but maybe this is the answer, or maybe this number 1 is the answer, exactly where the robot is. But with this resampling technique, I'm losing all those particles, other particles. But what's the benefit? Why I'm calling not only problem but also benefit? The benefit is looking like this. Then you discarding other ones. Then although this sample may be choosing 3 times, this sample may be chosen 10 times, but it's more likely representing the robot. That's the benefit that we have, the idea that we have to use it. But also we may have that problem. And also we will soon see in a second that how we can deal with that problem and propose some solutions for particle filter technique. So resampling step is probabilistic implementation of the Darwin idea for survival of the fittest. Since you don't, so let me a little bit explain this. It's very also interesting. So let's say in human population, we want a specific answer. Like you are looking for Superman, or you are looking for, let's make it more meaningful. So let's say we want a person who is 3 meters high, specific red eyes, red hair, and skin color is, I don't know, yellow, and what else? And bodybuilding guy, also can run very fast. So those characteristics, almost we don't have any person like that, right? So with evolutionary algorithms, we can say, okay, let's talk about current human population and control kind of next population based on who have more chance to be like that person. Then only those people will survive. Who has like color, eye color that is red maybe, is more chance, or colored, or who is like taller, whose skin is yellow, or we are very specific characteristics that we have for. Then we control who survives. And if you do that thousands of generations, you finally will have the answer. And this is evolutionary algorithms. For example, if you look at the families of cat, let's say at the beginning there was an animal that we wanted to find lion. And if the lion was the objective that we want to control the whole evolution, and if we would control it, we could control it, we finally can end up with lion. And this can happen really in simulation. And now millions of problems, thousands of problems that were not solvable can be solved with this technique. You define your population, characteristics of the problem, each one represents one answer. Then you say, okay, I want this exactly end answer. You define it, what you want. Then you let it to iterate millions of times. They of course, they marry each other, they have children, then you control that, you control mutation and control next generation, and you do the selection also. Selection comes usually based on the who has higher probability to closer to your answer, that you write a fitness function for that. Then later you have the answer that you want. For example, we can solve 8 queen problem with this, n queen problem with this. There is a chessboard. You need to place, for example, if 8 times 8, you need to place 8 queens. None of them collide with each other. This is 8 queen problem. If you try that, you may think that's simple, but you can try with soldiers to place it. That's not that easy to find even for human. You can find 1, you can find 2, but if you don't know the technique, you cannot find 26 different, for example, 30 different combinations. But evolutionary algorithms can find it for you. That 8 times 8 is okay, but 100 times 100 for human almost impossible. That's super difficult, but evolutionary algorithms are able to easily solve these problems. So now having this in your mind, also you can kind of develop that idea to generate an SLAM problem and see if we have all offline SLAM, then of course we can find the exact solution. If your robot moved in the environment for 1 hour, 2 hours, then you have the data. You don't need to onlinely construct it. Then you have this, you can use something like same idea to bring it to SLAM problem and solve full SLAM problem as optimization problem and have the exact pose in the where the robot position was all the time. So that was why I explained it a little bit, but not only there, in other techniques too. But one point that keeping your mind, this is not online basically, because this needs generations to let it develop. Algorithms like artificial neural network is in online. You can directly ask and get the answer, but here we should wait. It usually takes 1 hour calculations, few hours calculations in order to find answer for them. So if we come back to the course, we say instead of keeping all particles, we actually use the one that has higher probability that we discussed. On the other hand, now if you want to improve the Roulette field technique a little bit, this is common to use in particle filter, low variance resampling production, that with low variance resampling production, the point is, okay, instead of having one single point, that if we rotate it too many times, instead of having this, if I rotate this 10 times, maybe all 10 times I choose number 3, right? But with low variance resampling production, we can say, okay, let's put multiple uniformly distributed points to my wheel, then when I'm choosing one, I'm forcing to choose another samples from another locations too. So that here, if you choose one, rotate 10 times, not only you have to choose one of the particles from this guy, number 3, but you forced to also choose one particle from number 1. There is no way. But of course, it's still that one will choose more maybe than this 1 and 3, because we'll be choosing 1, 2, maybe 3, 4, each one of these 2 times more, but sometimes even missing this. And sometimes only can choose it with this idea. This is called low variance resampling, that is very common to use in particle filter, and it looks like this in implementation. You have the, of course, we want to choose based on the W's, and these W's can be distributed in this, some of them bigger and based on the weight that we have. Then with this simple equation, you can create these pointers that added by sub-constant values and distributed based on the size m that we have. This equation can give you the each one of the points are added by m to the power of -1, so that m is the number of the particles that we have, that each one based on the w. Then we solve that problem of losing the particles. And the implementation looks like this: low variance. We have set of particles. You get the random number at the beginning as r, then creating a for loop that calculates the same equation, r added by m-1 to the power of times to the power of m-1. Then there is a while loop that says while s is greater than c, do this and choose the particles up to end, like moving from here to here, and get the particle and add it to the c, and finally add that particle and return it. The implementation algorithm of the low variance resampling. So what we have important point here, we're selecting a sample with probability proportional to the sample. Weight is still because as I explained, the weight is higher, more likely still the low variance sampling will choose more particles from that set. So the advantage I almost already explained. It covers the more systematic fashion of the resampling, and if all the samples have the same importance factor, what will happen? Then we don't lose any sample. This is also nice explanation. So if all of these are same probability, then of course we should not lose any because they are same. But with the other roulette wheel, we will lose some because that's just random. But with low variance, all of the particles that if they have, all them are with same probability, will move to the next generation, next set of particles that we have. So we say if there is no observation, sampling step estimation also can be wrong because then we don't have observation, and of course the probabilities have been changed. And if there is no observation, then robot location is changed, and the selection will be based on previous observation. So robot from here moves there, but choose the particles from there instead of giving more weight to here. So that's also a point in particle filter. If you implement technique, the robot is moving in the environment and is not observing, detecting features that you want, then the observation, the estimation will be wrong. It's not like in unscented Kalman filter, you don't see it, just the error is increasing. Nothing wrong is happening. In unscented extended Kalman filter, if you don't observe, just your error is increasing, but here, no, that can be wrong. So what is the target distribution in importance sampling? Let's now see how we can choose the distribution based on the probability. We say density function f of probability distribution can be shown as this graph, this f, and this is the density distribution. And we would like to achieve distribution that we want to achieve this distribution that maybe is not that easy to calculate it. How would you like to calculate that one from the f? If it's Gaussian distribution, we can sample from normal distribution, then that's easy. But from this function, sampling, although it is there, but how you want to sample, that's difficult to do. That's maybe also not possible to do because this is a function, and sampling where is the peak, you don't know exactly, is nonlinear. Then you need to do lots of calculation, mathematical, find the and if we would solve that, we could use it in particle filter, in unscented filter or extended Kalman filter. One of the solutions is importance sampling. There are multiple solutions to do this. One of them is importance sampling, but with importance sampling we can merge two steps of localization for motion command and observation together. Let's see how it can be done. Easily we can generate particles from density such as G, we know. So since this is normal distribution, Gaussian distribution, we have in Python also functions, and we can simply do that based on mean and covariance. We can create this. That's okay. But how to generate f? So first of all, we say, okay, let's call this this distribution as proposal distribution, that we can write NumPy random normal to generate it for the prediction. And I put the link if you want to study more about how you could do that with different ways. You can have a look at this link for G. So if we consider this is as proposal distribution, now we can we want to calculate f using kind of this G. How we can do that? We can offset the differences between those particle weights, so that now we can say, based on the let's see how we can have these particles. We can say, okay, let's say the differences of G and F gives me the weights of each one of these. In order to do that, how we can do? We can write W of the M is equal to the particle that comes from distribution F divided the particle that comes from distribution G. And if you divide F over G, then you will achieve these weights over the particles. That if you do that, then we can say we have the belief of the xt and belief of the predicted xt. That here G is the predicted belief and F is the belief itself. If you remember, we were saying predicted belief as first step is coming from motion command. So it means that I was calculating predicted belief. Robot is moving, I'm running motion command and writing predicted belief is equal to the motion command that I run. Then I was updating that. So here the Gaussian distribution as G can be considered as the motion command, that we call it as belief of xt, the distribution that represents belief of xt, and we have this distribution over that as particles. Then we can calculate the weights based on the observation. That observation, for example, can be nonlinear function. Then this observation that is nonlinear, if you divide F over G, then you get the weights. That these weights actually giving you the weights of the particles that you wanted to have in order to give the weights over here to move to the next step. Understanding this is a little bit challenging. You need to focus and think about it because it deals with 2-3 steps together, but general idea is bring the belief and predicted belief all together in form of particles, and at the same time calculate also the weights. So for example, one also point here, tricky point here in implementation, if you think about, okay, let's say this value like f of the x, whatever the value is, if you divide it on this one, like 0.3 divided by this one, has higher than if you divide this part over here or this part over here, then you have lower weight over here. But if you consider, you may say, okay, maybe these moves in next steps and they come together. But if you divide that one to that one, the value is lower than the value that is you dividing here in mass. And that makes confusion for you, but you should consider that you should normalize each time independently. The values in each one can be different. So in time xt, you calculate these weights. The values cannot be compared with the next step values that you can get from here. You should normalize it also each time. Okay, any question? Simply, weight can come from F and G. F represents belief of xt, and G, belief of predicted belief of xt. That's it in implementation for particle filter localization. Now let's see a visual example. This is the environment. That's the robot position, for example, and from a starting point, robot has moved. And this is representing office environment of size like 54 meters times 80 meters. Then what is happening? We distributed lots of particles in the environment, on the environment. Then robot moves. After robot moves, observes the environment, and you can see that we have particles over here. And this is real robot position that we know. What happened from next step? We run all the things that I explained to you with particle filter, and the particles come to the next step that have higher probability to be here. And says maybe robot is here, 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 here. Why these are these also are existing as particles? Because of similarity of this area based on the error of the observation. The observation model that we had says most likely this one or this one can be the robot location, or this one can be the robot location. And that's like kind of interesting, and you see that we don't have known correspondences, for example, in here, and the particles are representing the robot position. And after moving more, then you can see that since the observation sees more identical features over here, then robot position more likely is something in the center of the particles that we have. Okay, clear? Now what problem can we have here? State a problem here in these three slides. A new challenge. Let's say we run the particle filter, as I explained, and robot is now here, particles are here. Create a problem. Also in chapter 1-2, I introduced the problem of the SLAM that it is valid here too. Make something that this algorithm won't work. Yeah. Yeah, kidnapping problem. Exactly.
Then the cloud of particles is
Yeah. We have kidnapping problem, right? We said kidnapping problem in robotics and Islam. is mean we catch the robot, put it somewhere else, kidnap it. So now if we remove the robot from here and put it here, then the algorithm is like particles were there and robot is now somewhere else. And is it able to find it? No. What we can do, now propose the solution.
The clone is too different from the observation, I will do a uniform distribution of the particles.
Reset the environment.
Start from zero.
Yeah, but that works, but that's not good idea. Better to have better idea. Because maybe the observation is kind of new, then although that is correct, but it's resetting all the time. That creates lots of another problems also. Better idea. Ilham, better idea. Rifki, better idea. Simon, better idea. Kick Simon. You can wash your face if you're sleepy. So the idea is, okay, let's say, in next slides we have it, but let me explain it here. Let's say at some time, although I'm more certain that robot is here, but and I can calculate the mean and covariance for robot location, right? That's fine. But sometimes if I distribute some seeds, a little bit of seeds in the environment, what happens? Most likely my mean and covariance is still the same, but I give more chance to other particles. If suddenly kidnapped, then more likely that particle get high weight, and from there they will be vanish and come here, like what happened here. Like at the beginning distributed, then this one, those other ones vanished because of these ones that gain more weight because of the movement and observation. So the same scenario can happen if you distribute some particles at some time, very low amount, but you give chance to check the other ones to weighting, and if that's the case, then this over here will have more accuracy if kidnap is happening. So it is called recovery from failure. Recovery from kidnapping problem is a challenge, and particles can survive based on that. We discuss it. Algorithms may accidentally discard also. That's another problem, not only by purpose, maybe accidentally all of them discarded. During resampling problem, resampling procedure, even if we implement low variance, maybe we have chance to lose them, and we can use simple heuristic to solve that problem, not only doing that uniformly resampling, uniformly generating new samples in the environment, but also we can use heuristic techniques. Heuristic in artificial intelligence means that we have a simple algorithm that is search technique and search the environment and gives a value to evaluate the situation. This is called heuristic in artificial intelligence. If you we discuss it a lot there, but simple heuristic we can call also greedy technique, like for loops that search best optimum and puts there. You can write some code examples to maybe smarter even put new particles there in the environment. So that can be called as technique that can solve the problem. And as I mentioned, one is the heuristic adds random particles. Also, we say even the kidnap problem, if it's not happening, we are sure that is not happening, still this technique can increase the robustness of the algorithm of the particle field. So, but here we have two questions now. The question first says, how many particles should we add at each iteration? How many new particles now we need to add in new iteration? Yeah.
Can you add the number that vanished with the resampling to keep the same amount of particles?
Something like you want to say something like static value,
Yeah.
depending on the beginning particles that I have. Yeah, that's one way to do that. We can say one approach might be a fixed number of random particles at each iteration. What else?
No, what I mean is you keep the total number of particles the same.
Mm-hmm.
So every time you do the update where you remove some particles, you use the removed one to put them in place.
You use the remove ones as new ones. Yeah, it can be that one too. But remove ones maybe also lost the thing, randomness. That has another problem. Then better to create new random one, or use heuristic to inject new smarter ones. Another way is like better idea to use articles based on the some estimate of the localization accuracy and based on the observation. It means that your heuristic can say my observation sees environment looks like this, and better then add particles around that part of environment that looks like that area. Like if we go here, for example, like let's say, so your observation sees something look like this, then better to add particles around here rather than adding some random particles around here, because you know that you're seeing your robot observing this area, this landmark or whatever, then better to distribute new random particles around here instead of somewhere far. Okay, clear? And second question says, so that's not very important. And from which distribution should we generate these particles? From which distribution? We can say new particles can draw in according to uniform distribution, as we discussed, and new particles can be directly distributed according to the observation likelihood that I answered already. So now let's say when to use particle filter instead of unscented Kalman filter. What do you think? What do you think, Tony? So now you have two options. You learned particle filter and you want to do it as project unscented Kalman filter. But if you are interested in, you can do particle filter too. So when to use particle filter instead of unscented Kalman filter? What do you think? So we had a professor who he was like, if somebody is a little bit sleepy or something, he was like, okay, I'm asking a question, then if a guy is not answering that question that is related to course, then all the class members will get negative mark. Then that was like serious rule. Then no one would even imagine to get close to be sleepy. because if you lose your own mark, that's fine. That's your own mark, right? Then you can give it up. But you're losing whole class mark. So, but yeah, imagine like studying like that whole semesters. And I think Ugo has some experiences. He's laughing. Yeah, I see. So if there is high amount of nonlinearity, of course using particle filter is useful, because we don't have that complexity anymore. You remember that we were struggling equations, doing from nonlinear problem to bring it to linear problem. That was difficult, but here it is easy. We didn't do too much complexing, just simple technique we've done. And of course, based on the number of particles, the computational cost is also increasing here, and it is much more higher than parametric technique. Then we need to also think if we have computational limitation, you are going to run your code in the embedded system, then number of particles if increases, then that's highly costly in comparison to UKF, for example. Because why? Because there we were just keeping one mean and covariance for all environment. We were keeping one mean and covariance, with robotics. But here we have like 100,000 of the particles. Then particle filter is not good for big space dimensions because of this problem, that if the big space is big, then you may have millions of. Then you want to localize in city. You cannot put 100 particles, 1,000. You need 1 million particles, maybe even more. Then the big dimension is still the other techniques, for example, UKF is useful. So how we can solve this space dimensionality problem? If we solve that problem with particle filter, we end up with new technique that is called FastSLAM. FastSLAM is very sweet technique. Why? Because instead of estimating each landmark with particle, we can, that increases the dimensionality, we can use the previous algorithms. For example, EKF can be used. How does it look like? Let's have a look. We say, okay, we have particle 1, particle 2, particle n. So that each particle has x, y, theta, and the landmarks, number of landmarks. Now we can use extended Kalman filter localization instead of particle filter idea. What does it mean? It means that I can say I have particle number 1 that includes this data for me, x, y, theta, and robot, like let's say this x, y, theta shows my robot is here and heading this direction, and these are some obstacles. Then particle 2 looks like this, particle 3 looks like this. So I have the particles. Now I want to bring extended Kalman filter in order to calculate the particle 1, 2, 3. And then I don't need too many particles. Instead of extended Kalman filter, we're running like only one scenario. I have couple of scenarios for extended Kalman filter with different noise, different initial poles, that each one leading to solve extended Kalman filter for this problem. That looks like this. For example, particle 1, robot moves with control command. The same control command from initial different positions. So we say particle 1 random position were here, this one is here, this one is here. We run the same control command on the robot, but the particle 1 moves like this, particle 2 moves like this, particle 3 moves like this. Then what I do, then observation comes, then I update the observation. Based on the observation that I can update particle 1, 2, 3, then this looks like this. The error per each one of these ones shows my observation. So that instead of having too many particles, I can have fewer, but in each particle, on each particle, I can apply one algorithm like extended Kalman filter. Or maybe wiser. This is called FastSLAM because it makes it faster, because using extended Kalman. Or maybe wiser, I can use, instead of particle 1 that is used by extended Kalman filter, particle 2 can be solved by unscented Kalman filter. Particle 3 can be solved by another technique. Then I'm combining particle filter with all the course that so far I've studied in order to generate and propose faster technique that is also more robust, that uses benefits of EKF, UKF, even Kalman filter, or different techniques that I can apply. Or for example, this can come from histogram filter, one of them. And this is called FastSLAM, and we have different techniques of FastSLAM. That's only I introduced one. So if you want to conclude, in this chapter we discussed about the particle filter localization, then we went through Monte Carlo localization. That was exactly the same, but practical way of implementation of the particle filter, and we introduced the low variance resampling, and finally we discussed how FastSLAM is working and how we can propose faster localization technique. So if you want to see the implementation, of course, the best example given by the Kalman and Bayes filter in Python book, that is interactive. You can have a look there. And we have also Python Robotics that you can have a look at some implementations examples, but be careful that the resampling step can be different, or weight calculation step can be different depending on different variations of implementation with particle filter. Also, I think, as I remember in the book, there are multiple ways, but exactly